no dependence on the mass. So it's remarkably powerful. This is a simple example, but further on in physics, you'll find dimensional analysis can be super helpful in just getting you some insight into what is the dependence of one parameter in some physical system on the others. Questions on this? Yeah.
Are there situations where when we solve these equations, the solution isn't unique?
Yes. And you can well imagine that. We happen to have chosen a particularly, let me say, straightforward and somewhat constrained situation. But of course, yes. I mean, you can imagine with just a few dimensional quantities to deal with, you can have multiple combinations of parameters that could give you the same outcome. So it's definitely the case that it can. And in some cases, you'll need to have additional inputs, and those additional inputs very often will come from experiments. So here, for example, I threw in mass as a kind of distraction, so to speak, because maybe it plausibly does depend on mass. But if you've done some experiments and you've observed the fact that it didn't depend on mass, you could throw that variable out. So it requires to do it at a more advanced level. It typically requires some further insights and further constraints. Good observation. Yeah. This one? Yeah. So this just means proportional to. And as we'll see throughout this course and throughout physics, when you've got something that's proportional to something, it means, for example, if I double the thing on one side, the thing on the other side doubles. So that's the idea of proportionality. And usually what we do in physics is when we've got a proportionality, we will replace it by an equal sign and some constant of proportionality. We haven't actually done it in this case. Dimensional analysis doesn't allow us to do it, but at least we've got the basic dependence from this. Yeah?
Can you explain again how you got from beta plus gamma equals 0 to 1?
Sure. So can I explain again how I got beta plus gamma equals 0? So,
And how you got that to 1 equals 8?
say that last bit again.
So how did you get from beta plus gamma equals 0 to 1 equals 8?
Again, I can't hear the last bit. Shout.
How you got from beta plus gamma equals 0 to 1 equals -2.
Okay. So these, okay. These don't, not good notation here. This doesn't follow from this, and this doesn't follow from this. So let me quickly recap. First off, we were looking at this equivalence, and we were looking at the dimension of mass, which appears on the right side to some unknown power alpha. And we have to demand dimensional consistency on both sides for an equation to be correct. On this side, m doesn't appear. So another way of thinking about that is on this side, m is raised to the power 0. Okay? So that tells us by just doing the comparison of the mass dimension that alpha equals 0. Possibly simplifying, I hope it wasn't confusing, I simply dropped n over here because we've already determined that its coefficient alpha is 0. And then I just concentrated on what's left, L to the beta, and I opened this out so that it's L to the gamma times T to the -2 gamma. That's just opening this term out. And then what I'm doing is comparing, in the case of beta plus gamma, I'm looking at the dimension of length. So on this side, I've got length to the power beta times length to the power gamma. And you know when I'm multiplying powers, exponents, this is the same as saying L to the beta plus gamma. So on the right side, I've got L to the beta plus gamma. And again, on the left side, L doesn't appear. So its coefficient on the left side better be 0, because it's L to the 0, which is 1. So that's where this comes from. I've got this is beta plus gamma, just by multiplying those two dimensions, and looking what it is on the right side. So that tells me that beta plus gamma must equal 0. And then the last one comes from the only dimension which actually does appear on both sides, namely t. And so here I've got t to the power 1. That's the 1. And over here I've got t to the power -2 gamma. So that's here. So this doesn't follow from this, but it follows from the thing up top. Once I've got this, I can say that gamma is just rearranging this, it's minus a half, and then I go back to here, and I've got, does that help? Okay. All right, so, it's something we're not going to make huge use of in this course, but it's a very powerful technique, and I wanted you guys to be aware of it. And I'm going to exercise you a little bit on it in the first homework question. Okay, so let's talk about vectors. We're going to use vectors throughout physics, starting immediately. And I'm imagining that most of you are pretty familiar with vectors. So somewhat in the spirit of a recap. Okay, so vectors are, by definition, quantities that have directional information associated with them. So they carry, it's kind of a weird word to use, but I'm going to use it anyway, both magnitude and directional information. It's the directionality that makes something a vector. Okay? So, it's pretty warm today. We might be talking about a temperature of 90 degrees. That is not a vector, it's a scalar quantity. It's a quantity that has a magnitude only. So temperature is a scalar, it's not a vector. But a sort of directional information to somewhere, like I'm going to direct you to Joe's Cafe after class. It's not very useful for me just to give you a distance that you have to go. I need to give you some directional information. So a displacement, which is a change of position, carries some directional information. So it's the directionality that makes something a vector. All right, so I'm going to try and be relatively fast on doing a quick recap of vectors. So let's think about notation. So I will use what I think is by far the most common notation for vectors. So some parameter with an arrow on top of it. And again, that arrow is supposed to remind you that there's some directional information embedded in this. So it might be some generic vector. Later on today, we'll talk about positions or displacements, and we might start to talk about the displacement, even something formed like this. A change in a position along an x-axis. A change in a position along an x-axis. So an x-axis, if you think about it, is all automatically carrying directional information. So indeed, this is a vector quantity. So notation-wise, you're going to see it most commonly with an arrow above the quantity. In some cases, in textbooks, you'll see it in bold font, something else. Various things, but that's what we're going to use. We're often going to represent vectors visually on diagrams, particularly so in a couple of weeks when we talk about Newton's laws. So I might represent the vector A by an arrow that looks like this. And if I was being accurate about this, the arrow would actually contain two pieces of information. Its length, if I was doing this properly, might be proportional, there's the proportional sign again, to the magnitude of this quantity. And of course the direction is very much important. So the length is important and of course the direction. So I'm very often going to draw vector diagrams and have arrows on them look like this. Okay, easy enough. So let's say I've got a quantity that I'm confining to be in one dimension. And I'm going to start introducing the idea of coordinate systems and axes and so on and so forth. We will very often use Cartesian axes coordinates, x, y, and z, that are perpendicular to each other. In fact, in this course, we'll mostly use that. So I might define a horizontal x-axis like so. It doesn't have to be horizontal. Also, it doesn't have to be such set up in such a way that x increases to the right. If I was perverse, I might set x increasing to the left. It's my choice, okay? But this is my coordinate system. We'll talk maybe a little bit more about coordinate systems, but what we need is some axis definition. We'll usually need some kind of defined origin. Let's call it O, why not? And probably we need to give it some sort of unit quantity. So it might be, we're talking about positions, for example, measured in meters from some origin O. So a coordinate system requires three things, pretty much: a direction, an origin, and some measurement of quantity, some unit I might now take my vector A, or not to be confusing, maybe I'll call it B, and it happens to be a vector that's pointing along the x direction, and it has a certain magnitude, presumably reflected in that length if I'm doing things properly. It's entirely possible that I might also be interested in the negative of that vector, negative b, and so if I was, I would simply flip things around, and it's a vector pointing in the opposite direction, but with the same magnitude, okay? So by putting a minus sign here, I just invert the direction. Fairly straightforward. Now, I can have these things represent a whole variety of physical things. We're going to talk most often early on about displacements, changes in position. So these may indeed be changes in position. It might, for example, be representing me pacing backwards and forwards along an x-axis at the front of the classroom. So you just saw me make a displacement, a change of position by about plus 5 meters in the x direction. But I could have the inverse behavior, which is now minus the vector displacement that I just before. It's a displacement of minus 5 meters again along the x-axis. So what this tells us is we're going to very often be adding multiple vectors. So this idea of superposition of vectors is going to be super important. Superposition just means adding in fancy jargon. And as you might expect, I can make multiple displacements and I can add them together to give me a resultant cumulative displacement. And I'm purposely walking backwards and forwards here to kind of give you the sense of that. I can add multiple vectors representing displacements together. And so, let me take this one step further, kind of a bad pun, but let me take this one step further and say that I'm going to start off with one displacement, which is maybe B, and maybe B is, in terms of magnitude, let me try and introduce a lot of things quickly. Let me say that B is 3 meters. This notation with vertical lines surrounding the vector tells us that we're talking only about the size or magnitude of the vector. So it's the size only, the directional information is forgotten when we worry about the magnitude. And let me say that there's a possible other displacement that I might make, and it's going to be represented by a vector C. Okay, let me say, for argument's sake, this has a magnitude 5 meters. All right, now, I'm going to have them both intrinsically be in the positive x direction. So there's C, and I've tried to draw the lengths of these arrows representing the different magnitudes. And as I said, I can of course do multiple vector displacements, one after the other, and ask the question, what is the end result? So this is simple addition of vectors representing displacements. And so what I can do, and I'll define this in just a moment, is I can first make a vector displacement represented by B. And I'm going to write B here with a positive, just to keep things clear. And I can do a second displacement represented by C. And the question is, what is the end result of all of this? We tend to call this in math a resultant, so I'm going to call it R, the resultant. It's simply the sum, superposition of two vectors. Okay, so you can imagine doing this. Here's my first displacement of 3 meters to the right, that's vector B. And then I'm going to add a second vector displacement of 5 meters again to the right, where I end up. So the resultant is the vector that gets you from the starting point to the ending point. And we can do this visually by the following. Take vector B. And when I've gone from here to here, I then add vector C. In order to do this visually, I'm going to put the tail of my C vector at the head of my B vector, like so. Hopefully that makes intuitive sense why I would do it. But I'm putting the tail of the second vector at the head of the first vector, and the resultant is the sum of both of So with the numbers that I gave you, it's pretty clear what this would be. This would be plus 8 meters, in this case, in the right-hand direction. Everyone okay with that? Yeah?
In the notation for the resultant, is that direction too, or should there be the absolute value or whatever, for the magnitude? Is it just the magnitude or is there direction for the resultant?
So there's definitely directional information in here. And that's sort of represented by the fact that I'm carrying the arrows. So good question, and maybe what I'm about to do will start to explore that a little bit more. But the directional information is in there. Okay, so the question then is what happens if I then ask, I'm going to do plus b. Now, instead of adding c as defined, I'm going to subtract vector c. Okay? So, b, as we originally started out with, 3 meters to the right. Now I've got c with a minus sign. And as we said a few moments ago, this just means I'm simply going in the opposite direction. So visually, I would represent this most likely like this. And not to be confusing here, I'm going to call the resultant of b minus c, I'm going to call it s. So rs following the alphabet. And s now is the vector that gets us from the starting point to the ending point. So there's s. So here's where your question about directionality starts to become relevant. Because now I've got this in the opposite direction. But it's still carrying the directional information. So what can you tell me would be the resultant displacement in this case, if I do plus b minus c? A little louder? Good. We're okay with that. All right. So, we're doing this in one dimension. What we're learning already are two things, I think. First off, we will often work with negative vectors, which simply means we flip them by 180 degrees or pi compared to their initial direction. So whenever you're subtracting a vector, just think of it as an arrow pointing in the opposite direction of the original one. What you can imagine, though we haven't explored this at length, is that it doesn't matter what order I superpose or add these vectors. I could have done c first, and then, or minus c first, and then b, or the other way around. And of course, if I have more vectors, the same is true. It doesn't matter. There's a word in math for that, which I can't remember. Commutative? I don't know. Anyway, there's something in math that means it doesn't matter which order you do it in. This is true, okay? It doesn't matter which order you do it in. All right, so not very interesting in one dimension. We need to make our life a bit more interesting and work in 2 or 3 dimensions, so let's start doing so. So, in 2 dimensions, let's make our life a little bit richer. So instead of me being confined to walking left and right along the line here, we're going to allow me to walk both left and right and forwards and backwards from your perspective. Unfortunately, I haven't yet mastered the art of moving up or down, so I'm going to do that in 3 dimensions. But let's stick with 2. So we're going to enrich our lives by adding a 2nd dimension. And so maybe, for example, what did I have? I had b plus c here. Maybe, first off, I'm going to make my vector b a little bit more like this one. So it's in some direction that is neither aligned with our x Cartesian coordinate, nor is it aligned with our y Cartesian coordinate. It's now in a 2-dimensional plane. And maybe I would have a vector c that is something like this. Why not? It's a 2-dimensional plane. The fact that I'm working in 2 dimensions doesn't change the intrinsic behavior of vectors, which is to say that I can still do multiple additions, often corresponding to physical displacements. And the question is, how do I figure out what the answer is? So, let's see. How do I want to do this? I am going to start off with this maybe in a slightly simpler way. I'm going to make this aligned with the x and y axes, standard Cartesian x and y axes. So x horizontal to the right, y vertical upwards. And I'm going to say, now that I'm going to turn this around a little bit, I'm going to make B be along the y-axis and C along the x-axis. So it's the same setup, but I just rotated it to be aligned with a Cartesian coordinate system. All right, so the question is, how do I determine what the resultant is here? So the same thing we could do graphically as we did a little while ago. What I really should have done here is actually, if I want to figure out the resultant, is I should have followed the same prescription and said, I'm going to take my first vector, displace myself from here to here, let's say, and then I'm going to take my second vector, put its tail at the head of the first one, and draw it like this. So that's following the prescription I have up there, and putting the tail of the second vector at the head of the first one. And then the resultant, if I was adding them, as I was up here, is the vector that points from my starting point to my ending point. Okay? So hopefully that's clear visually. I'm going to download this one because now I've moved it up here. So R again is the resultant. Okay, now, how would we maybe find the resultant? Well, first off, how would we describe the resultant? As with any vector, it needs to have a magnitude and a displacement. So with this particular setup, where I've chosen this in a Cartesian coordinate system, this is particularly simple because by construct, I've got a right angle here, and this immediately suggests that I can figure out the length of the resultant by using Pythagoras, and I can figure out the direction of the resultant, maybe this angle theta here, by using simple trigonometry. All right, so in this case, the magnitude of the resultant is presumably the sum of the squares of the magnitudes of the individual vectors, B and C, just making use of Pythagoras. So hypotenuse squared equals side 1 squared plus side 2 squared, because it's a right angle triangle. Easy enough, hopefully. And then the question of this angle, well, let's say I hadn't yet calculated R and I only know B and C. Looks to me like the tangent of angle theta. Well, here's the angle theta, here's the right angle in the triangle. The tangent of theta is the length of the opposite side over the adjacent side. So it's the length of C over the length of B. Okay. So that would allow me very straightforwardly to figure out both the magnitude and the direction of the resultant vector R. Yes, sir?
So about the notation, so when you say like R squared is equal to B squared plus C squared, you really mean like the magnitude, right?
Good. So I purposely wrote this because I kind of wanted you to be thinking a little bit about that. Yeah, I only care about the magnitude here. What you saw is I didn't put the vector notation there. What I could have done is this. So now it's getting complicated to look at, but it's the vector but the magnitude only. I might quite often, and I probably almost always will, simply be lazy and forget to put the arrow on here. So the suggestion is I'm only looking at the magnitude. And here I kind of did something hybrid. So it's a kind of typical laziness that I'll probably exhibit way too often. Yes? Good question. So am I always giving the direction with respect to, let's say, the north, in this case, vertically upwards? No. And that's something I'm going to want you to be super careful about in the first week or so, of course, because directions may be asked for with respect to anything, in fact. And in particular, I don't want you to get hung up on, and I see this quite often in intro physics, I don't want you to get hung up on the idea that X is always horizontal, Y is always vertical, and that angles are always defined with respect to the horizontal. That's probably what we're most used to, but it's simply a choice, it's simply a convention. And very often we'll mix it up in ways that, so things are defined differently. And so, let me just highlight what I mean by this. If I've got an angle defined with respect to the horizontal, then let's say we're about to do something that I was saving for a few moments from now, but let's say this is a vector D. the component of vector d on the horizontal axis, which we're about to talk about, is this. And you're probably used to thinking of this as d cosine theta, the length of this, which it is. So the only reason it's d cosine theta is because I've defined theta with respect to the horizontal. I could just as well define a similar setup like this. This is still d, but I could define the angle theta with respect to the vertical. And in this case, the component along the x direction is no longer d cosine theta, it's d sine theta. So we're going to talk about this a bit more in the future, but to answer your question quickly, it's not always going to be like that. Yeah?
We normally have an convention where we go with the adding vectors from head to tail, but then when we were getting S, we didn't do that at all. We did like tail to tail, and like I can understand why we do it, but I just would like to hear.
Okay, so the question was, did we do something different when we were doing S here? I may have gone over this a little bit too quickly, but in fact I still did tail to head or head to tail or whatever. Forget about this for a moment. What I was saying is that S is B minus C. So B is this one, its tail is here, but then I was going to add C, it happens to be minus C, so it's in this direction. But if you look at this, the tail of this one is at the head of this one. So I was following my description, whereby the second vector's tail is coincident both in the same place as the head of the first one. And then it's in this direction. So the thing that I suspect might have been confusing you is me drawing S here. And remember, S is just the vector that goes from our initial starting point to our final ending point. So I was following the same description there. Yeah?
Why did you fix C and B? You just be able to figure out the components of D to C.
Okay, so we're actually going to get onto that, and maybe see in a few minutes if you still have the same question. So we're going to look at components in just a moment. All right, so I think for most of you this is stuff you've seen before. We could find the resultant in the case where we've got two vectors at 90 degrees to each other simply by using Pythagoras and trigonometry. That's not generally going to be the case. And our vectors in 2 dimensions, there's no reason why they would be at 90 degrees to each other. So we need a more general tool, and this is going to be the tool of using components. So, what does it mean? It's pretty much what I started to do here, so let's do it a little bit more rigorously. We'll take some vector, let me go back to this one, B. And again, in this case, it's no longer along either the x or y Cartesian coordinates, it's just some general angle. So the question is, can we come up with a tool that allows us to do an easy way to add multiple vectors? And the answer is going to be most readily using this thing called components. And what does it imply? It means we're going to take all of our vectors and resolve them, which is the word that's often used, into components along our standard Cartesian coordinates. So standard Cartesian coordinates, here they are again, x in the horizontal rightward direction, y in the vertical upward direction. And we're going to resolve or project the vector into components along the x-axis and along the y-axis. So what does it mean? It means I'm dropping a line such that it intersects perpendicularly with the x and then the y directions. And I'm going to ask the question, what is the length of this component and what is the length of this component? The directions are already defined for us now, because by definition we're resolving them along the x and y axes. So this tends to get notated as the x component of vector b, and this tends to get notated as the y component of vector b. Another way of thinking of this that might be useful, it's like shining a light from way up here, let's say downwards on this, and it's looking at the shadow that this thing projects on the horizontal axis. And the same thing if I flip things around this way. So that's what we mean by coming up with components. So, how are we going to figure this out? Here's where I'm going to follow the standard convention and say that this vector b is oriented at an angle theta with respect to the horizontal x-axis. So this is the most common convention.